Okay, hello and welcome everyone. I'm Peter Robinson and this is the Ethereum Engineering Group Meetup. Today I've got Gary and Karim who are going to talk about bonsai trees and how they're going to improve performance for Ethereum. So Gary and Karim, before you share your slides, why don't you introduce yourselves?
Sure, yeah, I am Gary Schulte. I'm a blockchain protocol engineer on the protocols team at Consensus for Hyperledger Besu on the mainnet Ethereum team. I've been at Consensus now for about just a bit over 6 months.
And yes, Karim Tam, I have been at Consensus for 1.5 years. I'm working on the same team as Gary, so on the mainnet part of the Besu client. And before Consensus, I was working on some cloud-based payment solution. And yes, it's all.
Oh, thank you. So yeah, please share your slides.
Yeah, so this presentation is on a new data storage layout for Hyperledger Besu called Bonsai Tries. We're going to begin with a bit of kind of the state of Ethereum in general and the motivation behind Bonsai Tries in general. So a little bit of a recap for some of us, but just to kind of set the stage.
I don't think, can we see your slides? Oh yeah, we can. Yeah, no, it's all good,
okay.
all good. It's all just me.
Okay. So as Ethereum gains adoption, the network utilization goes up, the cost for block space goes up as well. And generally to address the rising cost of block space, we increase a network gas limit. However, increasing the gas limit, it also results in a growth of state, and not only a growth in state, but an increasing rate of the growth of state. And the larger this state, the more costly that state is to read and write to. And if you just look at over the years, I don't have data going back prior to 2019 because that's as far back as Etherscan happened to have. But you can see the gas limit increases from 8 million to 10 million and 10 million to 12.5 million. And then as you see now, we're getting quite a lot of critical mass in Ethereum. Even these increases from 12 to 12.5 million and 15 million and lately 30 million, they're eaten up as soon as that capacity is available. So as soon as we put more capacity online, the utilization goes up, and the more transactions there are and the more state there is to change, the more state there is to track. So briefly, the Ethereum world state is a mapping between addresses and account states. And the world state isn't stored on the blockchain, but the yellow paper specifies it should be implemented in a trie, also referred to as the state database or the state trie. The world state can be seen as the global state for Ethereum that is constantly updated by transaction executions. There's a couple of concepts here that we'll make mention of subsequently if you're not already familiar with state root, branch nodes, extension nodes, and leaf nodes that actually have the data that we're interested in on a per account basis. So today, Besu's world state storage is basically what we call a forest of tries, or we also call it forest mode. The underlying data store closely mirrors the Merkle trie data structure that each node in the with each node in the trie saved in a key value store by its node hash. Each subsequent block, the world state is updated with new leaves, new nodes, and a new state root. And old leaves and nodes underlying data store. And as this state grows and changes, this forest strategy leads to a couple of challenges. Traversing the trie structure gets slower and slower the deeper and deeper each state node gets, and the footprint for storing all of these individual nodes on disk, it grows substantially as well. So we end up with a lot of storage and a ever increasing cost of traversing that state trie. So what is Bonsai Tries? Bonsai Tries are a new data storage layout for Hyperledger Besu that aims to address these challenges. Bonsai encompasses a small set of philosophies. It is leaf focused. It focuses on well-manicured branches. It's focused on a single point in time. And this all results in reduced storage requirements. So one of the overarching issues is slow read performance. In Forest, when we are storing and accessing data by hash, in order to access account data, we have to climb the trie, so to speak. As we climb, we access each node along the branch in order to reach the account data. As I said before, as this trie structure gets deeper, the average number of accesses necessary to retrieve a single account grows. And if we have to hit, if you think about each node being a load from the data layer, that results in n number, or in this case, this particular example, 3 loads, 3 reads from the database in order to actually get to the account data. In practice, the Ethereum world state is much deeper and wider than this, and it ends up being substantially more reads in order to get to account data if it's not already present in memory. The Bonsai approach is to focus on the leaf data itself. Bonsai stores leaf values separate from the data, separate from the branches of the trie, also known as flat storage, where the forest mode must traverse all the branches by hash in order to read a leaf value. Bonsai can access the leaf from the underlying storage directly using the account key. Rates still have to traverse the trie to update the branch node hash values, but this strategy results in much faster reads of account data. The other overarching issue we're discussing is just the size of the database itself. The size of the database is always growing. Changes to a leaf node results in changes to the other nodes along the branch. Since in forest mode we store by hash, we end up duplicating the storage of the nodes and the updated branches. This results in a larger storage footprint and some orphan nodes as state continues along. You can see in the example here, block 175223, if we're making a single change to one leaf node from the value 27 to the value 45, we are updating not only the leaf node, but also B, the hash of B, the hash of 175, the hash of A, and the actual state root. So that single value encompasses all of these branch nodes along that path. The Bonsai approach is to have a single current updated trie. Bonsai Tries store the nodes by location of the node instead of the hash of the node. This allows for implicit lookup of old branch data. Implicit cleanup of old branch data. And when rewriting the branch, the old data is removed in Bonsai Tries. Prior states are retrieved by accessing the trie log layer and applying them to the current state to roll back, as it were, to a specific point in time, prior point in time. This way, we only end up storing one copy of the state trie, and that results in substantially less storage used, substantially smaller database. So I think a good way to think about Bonsai is to compare it to a similar function in Go Ethereum called Snapshots. Snapshots were introduced in Go Ethereum in 1.10. Snapshots are solving a similar problem as the tree traversal and read problem in a fashion that's not too dissimilar from Bonsai. What's a little bit different, though, is that Geth creates long-lived snapshots that also flatten account access to storage, but they're functionally reversed. Go Ethereum snapshots are taken at a fixed point in time, and they keep a diff log to roll forward that they apply on top of that historical snapshot in order to reconstruct current state. So the historical snapshot, the series of diffs are kept to apply in order to retrieve current, whereas in Besu, Bonsai snapshots are for the current point in time. The diff log is used to reconstruct historical state. This basically means that Bonsai is going to be fastest at providing the head state, and it's going to get somewhat, progressively slower at reproducing historical states the further back from head that you look. Conversely, Geth snapshots would more readily produce historical states, and read performance would get more expensive the further the distance from the snapshot to head gets. So as that distance increases, the cost would be more expensive to recreate current. They both result in faster read performance. It's just a little bit of a difference in that Go Ethereum is snapshot looking forward and Bonsai is snapshot looking backward. That basically that means that Bonsai is pretty much biased towards current. Another comparison, the trade-off with snapshots is storage. Unlike snapshots, Bonsai is a complete replacement for the Forest of Tries storage strategy. So Go Ethereum snapshots are supplemental to their existing try strategy, which is analogous to the Forest of Tries. And so that results actually in a net storage increase rather than a storage decrease. Even though it results in faster read times, it represents, like on mainnet currently, I believe it's an additional 15 gigabytes on disk. Besu's Bonsai implementation dramatically reduces the storage requirements because it actually replaces the Forest of Tries storage strategy. We only have the snapshot and the trilog layers for looking back. We don't actually, we're not supplementing the forest mode. We're actually replacing the forest mode. An additional, difference is that Go Ethereum requires explicit pruning to get rid of orphan nodes in old state, whereas Besu's Bonsai implementation is implicitly pruned because of the way the current state is maintained. This is a slide looking at the size of a forest node versus a Bonsai node for a full sync of Goerli. If you look, the forest full size definitely ramps up rather quickly as the sync progresses, as the blocks progress. And the Bonsai node actually, it does increase, but it doesn't increase nearly as steeply or dramatically. In this particular case, for the Goerli sync, we were seeing a roughly 5x for the full archive storage versus Bonsai. In other tests, we found actually a more substantial difference than that. We do have some limitations with Bonsai due to how the Bonsai implementation reconstructs history. There's obviously a cost to trying to reconstruct old state. If you need to look very far back in history, applying the trilog layers becomes successively more and more expensive the further back you look. We're looking into strategies right now to improve the look back performance, but currently, just to prevent having the node block on reconstructing historical state, we're limiting the trilog layer depth to 500 blocks for look back. Another consideration is that a Bonsai node can't really serve as a source for fast syncing nodes. Other nodes on the network, if they're looking to do a fast sync, since Bonsai stores data at a point in time, it's generally not a viable source for other nodes to use for fast sync. Fast sync messages request node data by hash at a point in time at the pivot block at which the fast sync starts. And inevitably that pivot block is going to end up thousands of blocks back from the current head during sync. And since fast sync data is requested by node hash, there's really not a cost-effective way to reconstruct that data from the trilog layer. If a historical node is requested by hash from Besu, an empty result is returned. We're planning to mitigate this by implementing Snapsync. Snapsync is actually kind of the successor to fast sync. And I think that Bonsai is actually well positioned to serve as a source for Snapsync. So we're not terribly concerned about not being able to support fast sync from Besu and Bonsai mode. And
So
I
yes,
will hand this over to Karim for some benchmarks.
So yes, after the implementation, we did some benchmark to evaluate the performance of the Bonsai feature, and we started to test a full mainnet node synchronization to see how many storage we need for the Bonsai and Forest implementation. So with a full archive Bonsai node, we found that we need something like 800 gigabytes. And for a full archive Forest node, we estimate that we need 12 terabytes. We also did a test with the 18 months old FastSync node without pruning, and it was 7 terabytes. So we can see an important difference just for a full archive nodes. You can go to the next slide. We also started to do some other benchmark, like started 2 FastSync nodes, one on Forest, one on Bonsai on the same pivot block and on the same AWS configuration to be sure we are testing the same thing, in order to see the evolution of this node after several months. After only 2 months, we found a difference of 554 gigabytes, and it was only 2 months. So we can imagine after 6 months, 7 months, the difference will be really huge. We also measured the disk usage between these 2 months after several months, and we can see in this diagram the stability of the disk usage for Bonsai and the evolution of the disk usage regarding Forest. So it's normal because, as Gary said, with Bonsai, we will access to the leaf directly. So the disk usage will keep relatively stable. And with Forest, we need to climb the tree. So when the world state will be bigger and bigger and bigger, we will access to a lot of tree nodes. So the disk usage will increase. If you go to the next slide, yes. We also checked how many blocks behind we had with these 2 nodes. And in this diagram, you can see that in green, it's the number of blocks behind with the Forest node. And in yellow, it's the number of blocks behind with the Bonsai node. During the test, we had 0 block behind with the Bonsai node. I will not say it's not possible to have block behind, but just during the test, we found that we have clearly less block behind with Bonsai. And yes, it's normal. It's still normal because we will have access to the data quickly. So we will have to process the block quickly. And so we will have naturally less block behind. We also found some fasting optimization. After several synchronization, we can say that the fasting with Bonsai is clearly 11 hours faster than Forest. So for the same reason. And we don't only want to improve the fasting duration. The next step will be to implement Snapsync. So you can switch. Yes, we want to implement Snapsync because Gary said it's difficult to be a source of fasting for other node with Bonsai. So we want to implement Snapsync, and the main idea of Snapsync is to, instead of downloading all of the tree node, we will just download the useful data and we will reconstruct the Merkle tree locally. So we will reduce the number of packet exchange between the node. So the snap synchronization will be faster. So we started the implementation of that. So it's only the beginning, but we hope to improve clearly the synchronization performance after this implementation. And with the Snapsync and Bonsai, we will have, we hope, less storage needed, less disk usage and faster synchronization. So Bonsai is still an experimental feature, but clearly we are confident because we did a lot of tests. We have a lot of canary nodes running since more than 1 year. So we are clearly confident and we hope to remove the experimental flag as soon as possible. And maybe when Snapsync will be implemented. So yes, it's the end.
Yeah. We aren't quite GA yet, but we're hoping to be there soon. And Snapsync, we think, will be what we need to in order to remove that experimental flag. And that's the end of the presentation. So if there's any questions, we'd be glad to answer them.
Well, thank you. Does anyone have any questions? But I know I've got a few, but before I dive in.
I suppose I always have a question about how does it relate to ETH2, any sort of considerations there or implications of the change?
Yeah, the Bonsai will work well in the execution engine. It basically becomes an execution engine in the merge. Where we'll probably need to have some rework is in state expiry, which is still a future speculative feature for Ethereum. We'll probably have to either rework or maybe isolate the initial state to be Bonsai only, because Vertical Tries probably aren't going to work exactly with the correct, work with Bonsai specifically. So we'll have to do some retooling for state expiry, but Bonsai should be fine for now, for at least I imagine a couple of years, because state expiry is still kind of on the horizon. As far as ETH2 though, yeah, Bonsai will continue to work excellently during the merge.
And our other Ethereum clients, I guess, are they looking to use the Bonsai technology?
I think Geth's snapshots are probably going to be their version of it. They were a long time in coming, and I think that they're pretty happy with that implementation at the moment. I think I haven't completely grokked what's going on with Aragon's data storage, but looking at it at a high level, it looks like they're doing something similar with a changelog that's account based. So it's on our list of things to do to see what Aragon is doing, and do a comparison and a contrast there.
Yeah. So do you think on average the Bonsai works out being more efficient than the thing that Geth has done? Do people want current state more than they want previous state?
I think for the common case, yeah, I think most people are interested in current, especially anybody who's like running an ETH2 node. They're interested in current. They're not interested in historical. There's definitely other cases, like a Block Explorer or Etherscan or something like that, that's going to be a bit heavier on prior state. But I think most use cases would be served by a view of current.
And it's something we want to measure. It's to benchmark the difference between Get and Bezo to see how it's perform. What is the difference regarding the performance, and to have more clear data, clear metrics to see when you need to use Bezo and you need to use Get, because I think we can use Bonsai for specific use case. You can use Price for specific use case. It depends on what you want to do with your client. And as Gary said, for an explorer, maybe Bonsai node will not be the solution. But on a lot of use case, you don't need to access to a very old blocks. So Bonsai will be sufficient.
Sounds good. I mean, I can imagine you might want to run, say, a call function, so a view function against, say, the version of Ethereum, but 10 blocks ago or 12 blocks ago. So whatever you deem to be the finality window for, say, mainnet. And so maybe people might do that, but that's still not that long ago, I guess.
Yeah, that's still well within the trilog layer limit that we've already defined.
But in order to implement this, do you have to have Snap syncing widely implemented if it can't use Beam Sync or not suitable for Beam Sync? Because that Beam works more like a snapshot, right?
Yeah. So a Bonsai node can fast sync from other sources. What it's not able to do is provide. It's not able to be a source of fast sync for another node. But I think generally speaking, you know, Snapsync is so much faster than FastSync that I just imagine that it's a feature that people will be wanting to use by default. The performance of Snapsync is substantially better. So it doesn't seem like a good use of time to focus on that particular use case as opposed to what was going to be the future.
Are there any other questions? Okay, could you go forward a slide to the forthcoming talks? Thank you.
Certainly.
Yeah. All right, so how topical it is that you were talking about state expiry only a few minutes ago. So on October the 27th, Raghavendra is going to talk about just that and try and say where things are up to and where things are likely to go. But before he gets to that, so in 2 weeks' time, I'm going to talk about the Poly Network hack and how Poly Network worked, why the hack was possible, what they could have done to try and prevent the hack, and just talk about, you know, essentially the bridge design. 2 weeks after that, I'm going to be also delivering another talk, which will be on the ERC20 cross-chain bridge using GPACT technology. And so for people who are going, I've got a great idea for a talk, as you can see in November there, we have 3 slots. So if you've got a great idea for a talk, please message me either on Meetup or LinkedIn or send me an email and we can try and set something up. So final chance to ask the 2 gurus about any questions about bonsai trees. All right.
When did you say it was going to be available?
It's available right now with an experimental flag, so you can actually use it today. But we're kind of gating going GA with that feature on having Snapsync implemented. So soon you can use it now, but it's still currently marked as an experimental feature.
And it can be modified regarding the Snapsync implementation.
True.
And I guess if you had it enabled, I mean, it's just something local to your node. So you can do it anytime you like, and it's not going to do anything with regard to other nodes in the network, is it?
Precisely. Yep.
So you turn it on, does it migrate automatically, the existing, and then?
No, you need to start a node in
Resync?
bonsai mode specifically.
Yeah.
Actually, does it affect the sync time? Because I know the sync time at one point was really, really long, but a big part of it was storing to disk. Does this improve the sync time?
Yeah, we noticed what about an 11-hour increase
For FastSync, yes.
or sorry, decrease in time for FastSync?
Cool, that's really good. Excellent.
Yeah, writes still have to walk the tree and make the same number of changes, but the reads are that much faster. So that's pretty much how we're accounting for that difference.
Yeah, and I guess the world will be a better place when that new sync mechanism comes in. So yeah, all right. Well, it sounds. And are you guys going to be the gurus on that new sync mechanism when it's you know, when we're all GA on that? And do you reckon you guys are going to come back and give us a good talk on that?
Surely. Yeah, Kareem is actually working on Snapsync right now.
Yes.
Fantastic. That sounds really good. All right. Well, look, thank you guys for delivering a great talk, and thank you everyone for coming along. And this video is going to be up on YouTube later today, maybe tomorrow. All right. Talk with you later. Thank you. Bye-bye.
Thank you.
Bye.
Thank you very much, both of you. That was excellent. Much appreciated. Bye.
Bye.